Hi friends, today we are going to solve LPP by graphical method, but the solution will be different. Now before that, let us understand what are the different types of solutions you will get when you are solving by graphical method. We have solved some problems by graphical method in our previous videos, and now what kind of solutions we have got there, and what are the different types of other solutions what we may get uh, when we are solving LPP by graphical method. Let us understand and let us solve one problem today on this LPP by graphical method. Let us see what are the different types of solutions we'll get. Now there are 4 types of solutions in linear programming problems through graphical method. Now all this time we have solved some problems where we have got unique optimal solution. Now what do we mean by unique optimal solution? A unique optimal solution where we get an x1 or x2 which is unique. It doesn't change, or out of, let's say we have a, b, c, d coordinates, we get just one coordinate we get. Now the other types of solutions what we get when we are solving LPP by graphical method are an infinite number of optimal solutions. Means we'll get more than one optimal solution which are infinite. Okay. The third type is an unbounded solution, and the fourth one is no solution. We may get no solution at all, right? So anyway, the previous videos, usual type of solutions what we get is unique optimal solution. These are very rare, and if we are getting such solutions, we should be able to identify if we are getting any of these things. Now the previous problems we have solved unique optimal solution. Now let us see these problems also, which are very rare, but you might get these kind of solutions also. So today we are going to solve LPP by graphical method, and we will arrive at a solution where we get an infinite number of optimal solutions. Okay, now let us see the problem. Okay, now need to solve the LPP, and this is the problem. Now let us start solving this, and we'll see the problem as it comes. Okay, now I've written down the problem here. Now when we substitute x1 as 0 and when we convert these constraints into inequality constraints into equalities, and when we start substituting x1 is equal to 0 and get x2, and x2 is equal to 0 and x1, we get the following coordinates. I'll directly write the coordinate because in our previous videos we have seen how to get the coordinates. Okay. If you don't know how to get the coordinates for these inequalities, watch our previous videos. Solution. Now I will write, there are 3 constraints here, 3 equations. So I will take equation number 1, and the coordinates what we have got for the first equation is 0, 500, and the second one is, it is 0, 200 and 0. For the second equation, what we have got is 0 for 50, and it is 300 0. And the third one, is 0 to 50, and 500 0. Okay. Now these are the coordinates what you have got here. Now let us see, let us try to uh, put a graph for this coordinates, these coordinates, and let us see what kind of graph we get. Now the highest coordinates what we have for x2 is 500, and if you see x1, the highest coordinate is 500 again. Now if you are taking this graph with this is x1, this is x2. Here it is, let us take each unit as 100. This is 100, 200, 300, 400, and this is 500. And take next to it is 100, 200, 300, 400, and 500. The first one, we have x2 as 500, x1 as 200. So I'm taking 500 here, 200 on x1. Okay, trying to draw a line. So this is equation number 1. For the equation number 2, it is 450 and 300. So 450 will be somewhere here. 450 and 300 on x1. Okay, try to draw a line here. And this is equation number 2. And the third one is 250 and 500. 250 is here, and 500 on each one. So 250 and 100. So this is equation number 3. So all the equations, what you can see now, we have to find the feasible region here. We have to find the feasible region. Now, to find out the feasible region, as we already know that we have to see the inequalities. Now, all the equations has less than or equal to sign. That means that all equations, equation number 1, say that the feasible region is below this, and even 3 says below, and 2 says below, and the inequality, non-negativity constraints say that x1 is greater than 0 and x2 is greater than 0. That means that the feasible region should be above this quadrant. It should be in this quadrant. So if we take the common area for all these 3 lines of 3 equations, now this is the feasible region. Now for this feasible region, we need to probably name the coordinates here. We have to name the coordinates. Now, the first coordinate, let us take it as O. Now, let this be A, let this be B, and C. Now, the feasible region is OABC is the region. Now, if we see the coordinates, we can write O. It is 0, 0. Now A is on the x1, it is 200, x2 it is 0, so it is 200, 0. Now B is in center. We will try to find it graphically. Today, instead of finding out the coordinates graphically, we will try to solve 2 equations to get the thing. I'll show you how. Now for C, it is x2 is 0, x1 is 0 and x2 is 250. So x1 is 0 and x2 is 250. These are the coordinates. Now all we have to do is we have to find the coordinates for this coordinate B. In such a case, when we are solving for B, we need to see, now B is an intersection for equation number 1, this line, and this line, which is equation number 3. So we are interested in equation number 1 and 3. Now we need to solve these two equations to get these coordinates. Either ways we can draw a dotted line and get the equations. But to get the accurate this thing, because we want to show here how the optimal solutions can be infinite. Alright. So now I'll take this thing off from here. Okay, and I'll take up this also. Okay. Now, if we are solving, I'll just take up the entire thing here. Let's have more space to solve it. All right. Now we are interested in solving equation number 1 and equation number 3, which is the intersection for B. So the equation number 1 is 5x1 plus 2x2 is equal to 1000. And equation number 2, for equation number 3, it is x1 plus 2x2 is equal to 500. Now, when we are trying to solve these two equations, we know how to solve it. We need to simplify it. Now, when we are simplifying it, solving these two equations, we need to see that we can take the one entire equation as in the minus sign. So on the both sides, if we take negative sign here, minus sign here, that means that 5x1 minus x1 will give you 4x1, 2x2 minus 2x2 is, you can strike it off, okay, and is equal to 1000 minus 500 is 500. So basically you got 4x1 is equal to 500, therefore x1 is equal to 500 divided by 4, which is equal to 125. Okay. Now basically you got x1 here, x1 is equal to 125. Now if you substitute x1 is equal to 125 in either of these equations, I think this is easy, so I'll take this equation, that is x1 plus 2x2 is equal to 500. I'll take this equation. Now I'll substitute the value of x1 here, that is 125 plus 2x2 is equal to 500. Now I'll take this 125 on the left side, that is 2x2 is equal to 500 minus 125, that is equal to 375. Now you can say x2, I'll take this 2 here, that is 375 divided by 2, that is 187 point. That is 187.5. So in this way we have got x1 here and x2 here. So we can, by solving these two equations, because these two equations actually meet here at B, so we are trying to find the coordinates for B, so we have got it. So x1 is 125, and x2 is 187.5. Okay, so now that we have got all the coordinates here, now we will try, now the optimal solution lies between any of these four. Now we will try to substitute all these four coordinates in the objective function to understand which has got the, since we are trying to find out the max value of z, so whichever gives the max value will be the feasible solution. Anyway, we will take the objective function, that is maximizing z, that is equal to 100x1 plus 40x2. Now if you substitute this for O, if you take O in the first place, if you take the first one, that is O, for O is 0, 0, if you substitute in Z is equal to 100 into 0 plus 40 into 0 is 0. Okay. Let us go take the second one, that is A, that is 200, 0, therefore Z is equal to 100 into 200 plus 40 into 0, that it will be 20,000, 20,000. Okay. Now the third one, that is B, that is equal to 125, 187.5. Therefore, Z is equal to 100 into 125 plus 40 into 187.5. Now, if you solve this, the answer what you will get is 20,000 again. Okay. Now the last one is C. The C coordinate is 0 and 250. It is Z is equal to 100 into 0 to 0 plus 40 into 250, that is equal to 10,000. Okay. So anyway, we have solved, we have substituted all the coordinates in the objective function. Now this objective function actually we have got the optimal solution here. Now when we got the optimal solution, now the maximum value of Z is at 220,000, which we are getting it here also and here also. So that means that the optimal solution lies with A coordinate as well as B coordinate. When we get some things like this, because we are taking highest value because we are trying to maximize Z here. The maximum value is 20,000, 20,000, because this is just 10,000, this is 0. So there are two maximum values here. So when we are getting two maximum values, we need to make we are sure that the maximum value of Z lies between A and B, and there is a line connecting from A and B. So there is a line connecting from A to B. So it's not just the maximum value is there on A or it is on B, but the maximum value lies between any point in the line which joins A and B. So if you take any point in this line, okay, and take the coordinates and substitute that into the maximum value of z, all you will get is the answer as 20,000 only. So, how many points will be there on this line? There will be infinite number of points. There will be infinite number of points in this line. So, it is called as. That's why this problem is called. Problem has infinite number of optimal. So, this problem has got infinite number of optimal solutions. So, I hope you understood this problem. We'll continue the next type of problem, an unbounded solution, in the next video. Thank you.